The uncertainty principle plays a central role throughout this framework. Position and momentum cannot both have precise values simultaneously. This is not a limitation of technology or measurement technique. It reflects the fundamental wave-like nature of matter. A localized wave requires many wavelengths, producing momentum uncertainty. A single wavelength spreads across space, producing position uncertainty. The trade-off is unavoidable because it arises from wave mathematics itself. This insight changes how we think about reality. Classical physics imagines objects with definite properties existing independently of observation. Quantum mechanics replaces certainty with probability amplitudes that evolve continuously until interactions occur. Reality at small scales is not composed of fixed trajectories, but of evolving possibilities, constrained by precise mathematical laws. Although this picture feels unfamiliar, it has proven extraordinarily reliable. Every experimental test, from atomic spectra to semiconductor behavior, confirms quantum predictions with remarkable accuracy. Technologies such as lasers, transistors, and modern electronics depend entirely on quantum principles. The devices shaping modern civilization work precisely because quantum mechanics describes nature correctly. And yet, despite its success, quantum mechanics leaves us with an unsettling realization. We know exactly how to calculate outcomes, but we still struggle to describe what is truly happening beneath those calculations. The theory works perfectly, even if our intuition resists accepting its implications. This tension between predictive power and conceptual mystery remains one of the most fascinating aspects of physics. By the time we reach this stage, the real lesson of quantum mechanics begins to emerge. The difficulty is not that nature is chaotic or irrational. The difficulty is that reality at small scales simply does not follow our categories, that our everyday experience prepared us to expect. We grow up believing objects have definite positions, definite motions, and clear identities. Quantum physics shows that these ideas are approximations, useful for large objects, but incomplete when applied to the microscopic world. What quantum mechanics ultimately teaches is that nature operates according to precise mathematical rules, even when those rules resist intuitive explanation. The strange behavior revealed by the double-slit experiment, the uncertainty principle, and indistinguishable particles is not a collection of unrelated curiosities. They are different expressions of a single underlying principle. Physical outcomes depend on how possibilities combine. In classical physics, events follow one definite history. A ball travels along one path. A planet follows one orbit. If multiple possibilities exist, only one actually occurs, and probabilities simply reflect our lack of knowledge about which one. Quantum mechanics replaces that picture with something richer. Instead of selecting one history before observation, nature allows multiple alternatives to coexist as amplitudes. These alternatives interfere, reinforce, or cancel each other until an interaction produces a definite outcome. This explains why observation plays such an unusual role. The important factor is not human awareness, but whether information about alternatives becomes physically available. If the environment contains information capable of distinguishing between paths, interference disappears. If no such information exists, interference remains. The behavior of quantum systems depends fundamentally on whether alternatives are distinguishable in principle. This idea often sounds philosophical, but it is grounded in experiment. Every version of the double-slit experiment confirms the same rule. Whenever path information exists, even indirectly, interference vanishes. Whenever distinguishability is removed, interference returns. The relationship is exact and measurable, not speculative. The universe expansion rate plays the role of initial speed, while gravity pulls inward. Depending on which dominates, our cosmic future changes dramatically. Physics describes three futures: expansion forever into darkness, a perfectly balanced flat universe, or a dramatic big crunch where everything collapses back together. This same balance determines the life of a star. Gravity pulls matter inward, while nuclear fusion in the core pushes energy outward. But stars cannot burn forever. Once their hydrogen fuel is exhausted, the outward pressure weakens, and gravity finally takes control. The star begins to collapse under its own weight, leading to some of the strangest and most dense objects in our universe. Right now, the universe is expanding, growing larger every second in a way you cannot feel, yet can measure with precision. Space itself is stretching, carrying distant galaxies away from us at thousands of miles per second. This expansion leads us back to the Big Bang, the moment billions of years ago when everything began from an extremely dense state. We know this because of redshift. The light from distant galaxies stretches into longer, redder wavelengths as they move away. The future of our universe depends on a cosmic tug-of-war between the force of expansion and the pull of gravity. Will it expand forever, or will gravity pull it all back together? Physics allows us to explore these extraordinary possibilities. Subscribe to our channel to explore more of the deepest secrets of our cosmos. The universe behaves like a ball thrown upward. The expansion rate is the initial speed, while gravity is the inward pull trying to slow it down. Physics describes three possible futures. In the first, expansion is so strong that galaxies drift apart forever, leaving each isolated in a cold, dark void. The second is a perfect balance, a flat universe where expansion slows but never stops, maintaining a precise scale forever. The third is the big crunch, where gravity eventually halts expansion, pulling the universe back into an extremely dense state. This fate depends on the matter we see and the unseen matter we don't. But gravity doesn't just shape the universe, it defines the life of every star. A star exists in a delicate balance, gravity pulling inward, while nuclear fusion in the core pushes outward with immense energy. But when the fuel runs out, fusion stops. Gravity, having waited for eons, finally wins, and the star begins its final dramatic collapse. Smaller stars like our sun end their lives gently. After shedding their outer layers, they leave behind a dense core called a white dwarf. Roughly the size of Earth, but containing the mass of the sun, these objects are supported by quantum pressure. Massive stars take a far more violent path. When they run out of fuel, their collapse happens in mere seconds. The result is a neutron star, a sphere so dense that a single teaspoon of its material would weigh as much as a mountain. But beyond a certain mass, no force can stop the collapse. Gravity continues to compress matter without limit. The mathematics predicts a critical boundary called the Schwarzschild radius. Inside this limit, gravity is so strong that space and time behave in radically unfamiliar ways. Crossing this boundary means no return. Light itself can no longer escape the pull. The star has become a black hole, a place where space curves so strongly that every path leads only inward. In the mid-1960s, physicists struggled with these implications. Some called such objects frozen stars because of how they would appear to distant observers. Others referred to them as black stars since no light could escape. Whatever the name, the theoretical predictions were profoundly strange. To understand why, imagine a thought experiment. Picture a massive star collapsing under its own gravity. Now imagine an observer standing on its surface as it shrinks, falling inward along with the collapsing material. At the same time, imagine yourself far away, watching safely through a powerful telescope. At first, everything appears normal. The star contracts and the observer moves inward. Light from the surface continues reaching you, carrying information about his motion. Perhaps he waves or sends signals. But as the star approaches the Schwarzschild radius, something unusual begins to happen. The light reaching you becomes redder and dimmer. This effect, known as gravitational redshift, occurs because light climbing out of a strong gravitational field loses energy. Its wavelength stretches toward the red end of the spectrum. The stronger the gravity, the greater the redshift. As the collapse continues, the effect grows more extreme, and alongside the change in light, another astonishing phenomenon appears. Time itself begins to behave differently. As the collapsing star shrinks closer and closer to its critical size, the effects predicted by Einstein's theory become increasingly dramatic. From your distant viewpoint, watching safely through a telescope, the observer standing on the surface of the star begins to behave in a very strange way. His movements appear to slow down. A wave of his arm takes longer than it should. Signals he sends arrive more slowly, stretched out in time. To the observer himself, nothing feels unusual. His watch ticks normally. His heartbeat feels unchanged. He experiences no sudden forces or warnings. But the light carrying information about his motion must climb out of an increasingly intense gravitational field. As it escapes, it loses energy. Its wavelength stretches, shifting toward red. The stronger the gravity becomes, the more extreme this redshift grows. Time near a collapsing star appears to slow. From your perspective far away, an observer's motions stretch out longer and longer as they approach the event horizon. Eventually they appear to freeze at the boundary, never quite crossing it from your view. This is why early physicists called these objects frozen stars. But for the observer falling in, absolutely nothing unusual occurs. They simply continue falling, unaware that space-time is curved so severely that all paths now lead inward. Once across the Schwarzschild radius, not even light can escape. The geometry of space itself traps everything, directing it toward the center. At the singularity, tidal forces become infinite. Here, our current mathematics breaks down completely, and physics as we know it ceases to describe reality. Both perspectives of an observer falling into a black hole are correct. They are consequences of how time behaves in strong gravity. General relativity tells us that time is not absolute. Near massive objects, time slows down. Even on Earth, time passes slightly faster for your head than for your feet. This gravitational time dilation has been measured with remarkable precision. Near a neutron star, 1 hour can correspond to 2 hours far away. The effects become truly extreme near the boundary of a collapsed star. From a distant viewpoint, an object falling into a black hole appears to slow almost to a halt, frozen at the boundary. These effects prove that time is flexible, shaped by mass and energy. But how do we detect these invisible objects? While light cannot escape a black hole, gravity still can. Gravity reveals the presence of what we cannot see. By watching binary star systems, we can see visible stars orbiting empty space, revealing the presence of these hidden cosmic giants. Of course, the space would not truly be empty. The motion of the visible star would reveal the gravitational pull of an unseen companion. By carefully measuring the star's orbit, its speed, distance, and period, astronomers could calculate the mass of the invisible object influencing it. If that unseen mass turned out to be too large to be a white dwarf or neutron star, yet produced no detectable light, it would strongly suggest the presence of a collapsed star. This method relies purely on gravitational effects. Even though the collapsed object cannot be seen directly, its influence on nearby matter betrays its existence. Many stars belong to binary systems, making this approach especially promising. Somewhere among countless stellar pairs, one star may already have collapsed while its companion continues shining normally. Another possible detection method comes from an effect predicted by Einstein long before collapsed stars were seriously considered: gravitational lensing. According to general relativity, massive objects bend the path of light traveling nearby. This prediction was famously confirmed during the 1919 solar eclipse. The purpose of physics is to follow evidence and mathematics wherever they lead, even when conclusions challenge intuition. Somewhere in the universe, massive stars are exhausting their fuel. Gravity is crushing their cores inward. Gravity does not merely pull matter, it reshapes space-time itself. As matter becomes denser, space curves more strongly. From a distance, a star appears to freeze at the boundary, its light fading. Yet for matter falling inward, time continues naturally. This is measurable reality. Experiments confirm that time runs at different rates depending on gravitational strength. As a star approaches its critical radius, paths tilt inward. Even light follows curved paths determined by the geometry of space-time. Physics describes reality as it is, not as we might prefer it to be. The universe is far more fascinating than it first appears. This fading is not because the star disappears instantly, but because time near the surface runs increasingly slowly relative to distant observers. Every process occurring there appears stretched indefinitely. To someone far away, the collapse never quite finishes. The surface seems frozen at the boundary, eternally approaching but never crossing. But from matter falling inward, events proceed normally. Inside the Schwarzschild radius, the structure of space-time changes fundamentally. Every possible path leads inward. The center becomes an unavoidable future. Falling toward it is as inevitable as moving forward in time. Escape is not prevented by a physical barrier, but by the structure of reality itself. Mathematics confirms this inevitable outcome. Meanwhile, the same gravitational principles shaping collapsing stars also govern the universe as a whole. Expansion or collapse depends on matter and energy. Gravity works everywhere, from stellar scales to cosmic scales. The predictions follow directly from tested physical laws. In a universe where expansion continues forever, galaxies drift farther apart until they become isolated islands surrounded by darkness. Over unimaginable timescales, stars exhaust their fuel, and new star formation ceases. The universe grows colder and emptier, approaching a state sometimes called heat death. Nothing dramatic ends existence. Activity simply fades away. In a perfectly balanced universe, expansion slows but never stops. Gravity continuously resists expansion without reversing it. The universe expands forever while approaching equilibrium, a delicate balance between motion and attraction. In a universe dominated by gravity, expansion eventually reverses. Galaxies begin moving closer together. Temperatures rise as matter compresses. Structures merge and collapse. The cosmos contracts toward a final dense state, a big crunch, possibly resembling the conditions from which it began. Which of these futures is correct remains one of the central questions in cosmology. Determining the answer requires measuring invisible components. Right now, galaxies continue moving away from one another as space itself stretches. We observe this directly through the redshift of distant light. The farther a galaxy lies, the faster it recedes. Running this process backward leads naturally to the Big Bang, a moment of extreme density and heat. Elsewhere in the cosmos, massive stars are reaching the ends of their lives as their nuclear fuel is exhausted. For smaller stars, the outcome is gentle, white dwarfs cooling slowly over unimaginable timescales. For heavier stars, the collapse becomes violent, forming neutron stars or even more extreme objects. For the most massive objects, the star collapses beyond the Schwarzschild radius, forming a black hole. These objects challenge our understanding because they follow the laws of general relativity so precisely. General relativity predicts that time slows in strong gravitational fields, and experiments confirm it. Near neutron stars, it becomes dramatic. Near black holes, time dilation becomes extreme. From far away, the collapsing star appears frozen at its boundary. Yet for matter falling inward, events continue. The boundary is crossed without notice, proceeding inevitably toward regions our current theories cannot describe. Time becomes a dynamic feature of the universe, shaped by gravity just as space is shaped by mass. Reality is not defined by a single universal clock. Events can unfold differently depending on gravity's pull. Global positioning systems must account for gravitational time dilation to function accurately in our daily lives. We study invisible objects through binary systems and gravitational lensing, where gravity itself becomes the messenger. Physics progresses by confronting reality honestly, even when the conclusions feel unsettling or challenge our intuition. The interior of a black hole remains one of our greatest open questions, marking the limit where our known laws cease. Yet incomplete knowledge at the frontier does not diminish the extraordinary success of the theories leading up to it. Every prediction about gravitational redshift, time dilation, stellar collapse, and cosmic expansion has been supported by observation. The framework works consistently across enormous ranges of scale, from laboratory experiments measuring tiny shifts in photon frequency to astronomical observations spanning billions of light years. The universe therefore reveals a profound unity. The same equations describe the birth of the cosmos and the death of stars. Space expands, time bends, and gravity shapes the structure of everything we see. These processes are not separate phenomena, but interconnected aspects of one coherent physical reality. When we truly consider what this means, the familiar picture of the universe changes completely. Space is not empty background. Time is not an absolute flow shared by all observers. Instead, they form a dynamic fabric influenced by matter and energy. Galaxies drift apart because space-time expands. Stars collapse because space-time curves inward. Observers experience different realities because time itself responds to gravity. And perhaps the most striking conclusion is this: the universe is stranger than it first appears. Not because it is chaotic, but because it follows deep mathematical principles beyond everyday intuition. The equations do not care whether their predictions feel comfortable. They simply describe what is. Some questions remain unanswered. Will the universe expand forever or someday collapse? What truly happens at a singularity? Does a deeper theory await discovery beyond general relativity? These mysteries continue to drive research, reminding us that physics is an ongoing journey rather than a finished story. What we know already, however, is extraordinary. Space is expanding. Time is flexible. Massive stars can collapse into regions from which light cannot escape. Gravity shapes the destiny of structures both immense and small. And by following mathematics wherever it leads, we uncover a universe far richer, more subtle, and more astonishing than common sense ever suggested. The more carefully we examine reality, the clearer it becomes. The universe is not simpler than we imagined. It is deeper.